PowerPoint template, PowerPoint PS6, PowerPoint show, save. Okay, got it. Let me see. Okay. Hello.
Hello, sir. We can hear you, sir. We can hear you.
Okay, but I see that you are not seeing my video, or you see my video, but not the full presentation behind.
Yes, sir. Just a minute. We'll resolve this. Just a minute. Yeah. Yes, sir. Now you can see.
You see?
Yeah. Perfect.
No, because it's completely black. You should see my video behind. You should see my video. I think you're just seeing my face, but not my video behind.
Yeah, video we can see.
Let me see. Window capture. For window projector. Well, a bit better now. Window PPSX automatic. Okay. Can we share? Okay. Hello. Now I think it's okay. The only thing I would like to know if you can listen to my audio, and another thing I would like to know if you see the pointer. You see the pointer on the video screen.
Yes, sir. Yes.
Okay, so I think that that would be good. There are still 14. There are already 14 participants.
Yes, sir.
You should ask me. You should say me when I can start with the presentation, so I will start with the presentation. And another thing I would like to ask you. You should reply me if you are still looking at my video now. Do you have the video screen with the title of the presentation, and do you have my image in the video, real-time image on the right side of on the right bottom side of the video?
Yes, sir. You can perfectly see in left side your image is there in the slide itself, and the right side your real-time video is there.
Okay, so I put the laser pointer here. You can see the laser pointer.
No, sir. You can't see your laser pointing.
Okay, there is a. So I think that now all is working well. We can start whenever you want.
Yes, sir. We will start at sharp 2 o'clock here. Just 1 minute for that.
Good afternoon, one and all. As we are about to begin, I extend my warm welcome to all of you to the keynote session of AIES 2021. The keynote speaker for the session is Professor Enrico Staderini, Director, Healthy World Association, Switzerland. May I now request Dr. Arun P., Associate Professor, Department of Electronics and Communication Engineering, to introduce our speaker. Dr. Arun, over to you.
Thank you. Anu, am I audible? Good morning, good afternoon, and good evening, ladies and gentlemen, wherever you are in the world. Once again, welcome to St. Joseph's College of Engineering and Technology. It's my pleasant duty to bid you all a genial welcome. Today, we are gathered here virtually to take part in the keynote on the problem of recording the instantaneous heart rate signal, which is scheduled as part of International Conference on Artificial Intelligence and Energy System 2021 at St. Joseph's. For this, we have an impeccable choice of tutor, Emeritus Professor Enrico Staderini. Professor Enrico holds MD degree from the University of Rome, Italy in 1981, from which he also got a post-graduation degree in biomedical engineering and a PhD in cardiovascular physiopathology in 1982 and 1988 respectively. Then he done another specialization in assistive devices engineering for the elderly and disabled people in 2003 from the University of Trieste, Italy. He also qualified as European certification for informatics professionals from the Council of European Professional Informatics Societies. He was a registered physician in Italy, Norway, and Switzerland. After a combined career in the medical practice, the informatics, and the biomedical devices industry, Enrico served as invited professor in India, USA, Brazil, Norway, the International Atomic Energy Agency governed by UNESCO, and as a researcher in Italy, teaching medical physics and biomedical engineering. He was the president of the Swiss-based Healthy World Association and the member of the International Electrotechnical Communication, the IEEE, the Swiss Society for Biomedical Engineering, the Bern-based Biomedical Engineering Club, and the Swiss Electromagnetics Research and Engineering Center. He also sits in various international and national experts panel and doctorate course. He served as the professor at Western Switzerland University of Applied Science and Arts in their Industrial Automation Institute. His main research interests focus on neurophysiology instrumentation, sport technologies, cognitive science, ultra-wideband medical radars, rehabilitation engineering, biomedical electronics, and assistive devices for the elderly and the physically challenged people. He has published more than 100 peer-reviewed scientific papers and directed important research projects. He is still active at the international level with very important and tight relations with Indian companies and universities besides others. Currently, Professor Enrico Staderini is the director at the Healthy World Association, Switzerland. It would be my greatest privilege and honor to welcome Professor Enrico Staderini to this session. Welcome, sir. Now, I welcome all the audience who took out time and energy to be part of this keynote session. Welcome you all to this online conclave. Wish you all a great time ahead. And now, over to you, Professor Enrico Staderini, and the floor is all yours. Thank you.
Okay. May I start now? Shall I start now? First of all, good afternoon to you all, wherever you are, maybe in India, maybe in other place in the world. And thank you also for the kind invitation of Professor Arun and your university. They are organizing the AIES 2021 International Conference on Artificial Intelligence and Energy Systems. My keynote lecture will belong to the artificial intelligence track of this conference, and most probably on the track 2, signal and image processing. And I would like to address today as a quite misunderstood problem, the problem of recording the instantaneous heart rate signal. Instantaneous heart rate signal is a signal of the heart frequency. So it's not the heart ECG or other signals, but it is the frequency of the heart, which is changing in time. That's why we can consider this as a signal. So I will start just to introduce you what is a signal, and then we will see how we can record this very strange kind of biomedical signal. Just to introduce the heart rate as a signal, we should consider one thing. What is the heart rate all about? And what I would like to show you is why is the heart rate signal such a different signal from other signals like acoustical signals or radio signals or whatever else, or pressure signals or whatever. And how can we use the heart rate signal in a classical way? We use other biological signals, for example, for creating time tracing of the signal or Fourier transform of the signals or any other thing. And what is the information that the heart rate signal will convey to us, and how we can exploit the information conveyed to us using the heart rate signal, and how we can extract such information. So most of the presentation will be devoted to the heart rate signal acquisition. And at the end, I will also show you an application that two of my students here in Italy. Now I am based in Italy, just for this presentation, but I will travel to Switzerland very soon, and I will present you these two students and how they are using the heart rate signal for a particular application. A signal, you know, is a variation of a quality of a given phenomenon. This is maybe the most comprehensive definition of a signal. And of course, a signal is signaling something. So a signal is also, in the variation of the quality, is also the signal a means to deliver or to transmit information. So variation means a variation in time or a variation in space. Most probably we are much more interested in a variation in time than a variation in space. But we can also consider an image as a signal, because in an image we have a variation in space of the light coming from different points on a surface, for example. That's an image. And the quality may be the magnitude of a given physical quantity which is linked with the phenomenon. So, for example, the magnitude or something, the magnitude of light coming from a photo, from an image, or the magnitude of pressure we can detect with a sensor. So this is exactly a signal as we commonly mean it. And more commonly, we consider a signal as a time description. So when you are thinking of a signal, you are always thinking to the tracing of a signal, in which you can trace the magnitude of a certain physical variable, for example, acoustical pressure or whatever, along the time, over the time. And most often, we don't use the signals directly. Instead, we use a sensor to convert a given signal from its original physical form, for example, acoustical, to a more easily manageable form, often electrical. And we use, for example, sensors. Well, at the end of this presentation, we will see that we will use the heart as a sensor for detecting a signal coming from the parasympathetic and sympathetic autonomous nervous system. So this is very nice. At the end of this presentation, we will see how to exploit the use of the heart as a sensor, because the autonomous nervous system is acting on the heart rate. And if we will be able to detect the heart rate as a signal, we will use the heart as a detector of the activity of parasympathetic and sympathetic nervous system, using the heart as a sensor. That's a very nice final result, conclusion of this presentation. So I ask you to be very attentive on how we can arrive to that conclusion. Another thing is the observability of a signal. Signals observability is that we can be able to trace a signal. So, for example, with a microphone, we should create an analog signal. Analog signals means that the output of the microphone, the output of the sensor, is an analogic representation of the signal on the membrane of the microphone. And in this way, the observability of the autonomous nervous system will be done using the heart rate considered as a signal. But the problem is how we can look at the heart rate. It seems very simple, but not as simple like this. Now, most signals are continuous, and they are continuous both in magnitude and in time. Of course, For example, if you consider the pressure of the acoustical pressure on the microphone, of course, the acoustical pressure on a microphone is a continuous signal in the sense that the value of this pressure can assume any possible value on a range of values. And if signals are not continuous, we say they are digital in the sense that the value, the magnitude of the signal can only assume one or two values or a finite set of different values. We can also consider signals which are not continuous in time or space, in the sense that they are discrete, and a signal is discrete when the observability of the signals is not always guaranteed, in the sense that the signal can be measured at a different defined instant of time, and between one sample and the other, nobody can yes,
Professor. Sorry to
please.
Sir, are you changing the slides or it doesn't saturate it?
But are you looking at the slides?
Yeah, no, we can see your slides as well, only the image.
Because I'm changing the slides.
Yeah, now we are seeing only the first title slide on the problem of recording the instantaneous heart rate signal.
No, that's a problem. I don't know why. You're only the first slide.
Yeah. That's only visible for this.
Maybe I can do another thing now. Maybe I can go on the being recorded. I got it. You can see only the first slide. Maybe I can share the screen. I can use this one. Allow. Now you should see the slide, the present slide.
Now, sir. It's perfect now. It's perfect.
Yeah. So let me see very fast. Go back so that you can have an idea of what I have. Well, until now I just presented very simple things. I discussed what is the heart rate signal. And then I discussed what is a signal, the variation of the quality of a given phenomenon. Then I presented what is a signal commonly considered, and then the observability, what is an analog signal, which is the analog variation of coming from a sensor. And then I discussed about the continuous in magnitude and continuous in time or space. And so I consider that if the signal is not continuous in magnitude, that is a digital signal. And if the signal is not continuous in time or space, it's a discrete signal. Now, what is the heart rate signal considering this? The heart rate signal is the heart frequency, no? The heart rate is the heart frequency, or the number of heartbeats in a given time epoch. Okay, it's a very simple description like this. But I just said that for me, a signal is a variation in time of some physical magnitude. Now, here, the physical magnitude is the frequency of heartbeats. So if we say that the frequency of heartbeats is changing in time, this means that we should measure the frequency of heartbeats at each instant of time, but this is impossible. Let me say, as the heart rate is quite slow, often the time epoch we use for heart rate definition is the minute. Thus, we can state that the heart rate is the number of heartbeats per minute. That's very simple and trivial definition. So we may have 72 beats per minute, which means 1.2 beats per second. So the heart beating at 1.2 hertz, right? Okay. Now, as the heart rate is varying in time, we may conceive a heart rate signal in the sense that now maybe my heart is beating at 1.2 hertz, and just a few seconds after, my heart beating at 1.5 or 0.9 hertz. So how we can create a continuous or at least a discrete signal of the heart rate. And what are the problems? The question is, the heart rate is a continuous signal or a digital signal or a discrete signal. We may say that maybe the heart rate is a digital, is not a digital signal, because the frequency can assume any possible value. But maybe it's a discrete signal in the sense that the knowledge, you know the heart rate only at each beat. You don't have any idea of the heart rate between any two consecutive beats. That's the problem. But we will come back on this question. Now, I would like to show you, just a restart from basics. So the problem with the heart rate is how to create the path from the heart to the heart rate. On the left side, I played the heart beating. On the right side, there is a standard, more or less a standard watch, very often used for detecting and showing the heart rate in beat per minute. Now, how we can go from the heart to the presentation on the watch? There are two ways of getting signals from the human body. One is known as sensing modality, and the other is a probing modality. In the sensing modality, you have some energy coming out of the body. This energy is detected by a sensor or transducers. The output of the sensor will be a signal. The signal will be processed, and at the end, we will have the heart rate. In a probing modality, we have a source of energy going into the body and being modulated by the body, and the sensor will detect this modulation, and then the signal and the processing and the heart rate will come out. You can recognize that in the sensing modality, typical sensing modality is the ECG, the electrocardiogram. In the electrocardiogram, you have an energy that is the electrical energy produced by the heart, which is produced by the body, and this is a typical sensing. You have a sensor here. In the probing modality, you may recognize, for example, the photoplethysmography. That is the detection which is often used by watches, in the sense that a light source is sent to the body. The light source is modulated by the perfusion in the body, and the modulation is detected by a sensor, a light sensor, and at the end we have the heart rate. So these two sensing modalities are quite important to understand. For the following, we will use the ECG as a sensing modality, because it's much more useful and precise. Then, how can we detect the heart pulse? Well, there are a series of physiological phenomena we can exploit. For example, we have initially the electrical stimulation of the heart muscle. The heart muscle will contract, and so we have the moving of ventricles and valves in the heart. And then the pressure will rise in the vascular system, and then the blood will flow into the vascular bed, and then the blood will perfuse the peripheral tissues. These are all the physiological phenomena. But at each physiological phenomena, we will have a physical phenomenon. The physical phenomenon for the electrical stimulation, we will have electrical energy produced. So we will have the electrocardiogram. For moving of ventricles, we will have a mechanical energy produced. So we will have movements of heart sounds. For the pressure rising in the vascular system, we will have a mechanical energy produced, so pressure in the vascular system. And for the blood flowing into the vascular bed, we will have a mechanical energy produced, movement, flow, or changing of physical properties of tissues. And when the blood will perfuse the peripheral tissues, we will have the changing of the optical properties of tissues. Of course, all these physical phenomena can be detected by a sensor, and from these sensors, we will have some information regarding the heart rate at the beginning. Now, this slide I think is very nice. It's very important because I put here all the possible detection technologies for detecting the heart pulse. You know, there is the heart sinus node producing the heart electrical signal. The stimulation goes to the ventricles. The ventricles will contract. with a fluidic signal will be generated in the vascular bed, or maybe the contraction will be fake hemodynamically, and so will be undetectable maybe at this time. The electrical signal will be detected with the ECG, and we will have an ECG tracing. The contraction of ventricles will generate a mechanical signal. We will have the movement of the wall of the ventricles, or the movement of the leaflets of the valves. And we can probe this using ultrasound, ultra wideband radar sound. So we will have the phonocardiography. I said this is a sensing modality, or we will try to use the blood pressure, the variation in blood pressure. So we will have the blood pressure propagation until the peripheral pulse, and we will detect the peripheral pulse at the end. Or we will have the blood flow, and blood flow can be detected using a series of different technologies, and eventually we will have the peripheral perfusion, and we will have some laser photoplethysmography or video processing, video perfusion system. There is a series of different devices for detecting at the end. From those signals, we will try to detect the heart rate of the heart frequency. Of course, I will share with you this image because it's quite interesting, because it's really complete of all the possible detection technologies. Another thing very important is the bandwidth of signals containing heart rate information. Here I put on a logarithmic scale of frequencies the bandwidth of each device. For example, for the ECG, the bandwidth of the ECG goes from 0.2 maybe to 75 or 80 hertz. And all the other devices for the phonocardiogram, for example, we are in the acoustical region. Ultrasound also comes in the acoustical region. But the heart rate per se has a bandwidth around 1 hertz, of course, because the heart is beating at 60 or 70 beats per minute. And the breath rate is even smaller, is around 0.2, 0.3 hertz. This is the breath rate. Okay, so it's important to understand what is the bandwidth we are using to detect a signal which is very limited in band and very low band occupation. Well, now repeating the question, is the heart rate signal continuous? Now, we actually don't know the instantaneous heart rate. Why we don't know the instantaneous heart rate? Because suppose the output of a microphone, you can you can record the instantaneous signal coming out of a microphone. That's completely clear. But you don't have a sensor for the heart rate in the sense that you have a sensor giving you the instantaneous value of the heart frequency, because it's a frequency. You have to wait the next beat to measure the last period, the last heart period. You don't have any possibility to detect, to know the heart rate between 2 beats. Of course, that's the problem I would like to address. So we just and only have the heart period, not the heart rate. And furthermore, we have it at each heartbeat, not between 2 heartbeats. So heart rate signal is a discrete signal. If we would like to record the heart rate, we can only record the heart period at each beat. But if the heart period, like the heart rate, is changing in time, this means that the heart rate is not uniformly sampled, because the sampling point of the heart rate are the heart rate itself. So the heart rate is a sampled signal, and the sampling frequency is the signal itself. Look at this. Now you see on the first tracing, the upper tracing, there is the ECG signal acquired with an ECG. So this is the ECG signal. It's a 2 minutes signal. And you can see that we found, with a particular algorithm, we found all the peaks into the ECG, and we found the position and age of each peak. Now, the age of each peak is not of importance because we are only interested in the heart rate, so in the heartbeat. So the only thing that is important to us is the position of each peak, position in time of each peak. And now, in the second tracing, we put the heart period in second during time. Of course, we have 1 point of the heart period signal for each peak in the ECG, and this value, the value of each point of the heart period, is nothing else than the distance in time between two consecutive peaks into the ECG signal. Of course, we can also consider the heart rate. We should consider instantaneous heart rate as 60 divided by the heart period, and so we will have the heart rate in beats per minute, and you can see that it's changing in time. The problem with this tracing is that in the first tracing, this is the ECG sampled at a given uniform sampling frequency, but the two other tracings are not uniformly sampled because we have 1 point at each QRS, at each ECG beat. And so you can see, for example, that the distance between consecutive peaks here in the heart period is not uniform. I will show better here. We can take a closer look. And now you can see, for example, for these two ECG, for these two peaks, there is a distance of 0.93 seconds. And in the heart period, we will have also a distance of 0.93 seconds between two consecutive peaks, because this was the first peak taken here. This is the second peak taken here. The distance between the two, of course, is the distance between two consecutive heartbeats, and the amplitude of the, because we are looking at the heart period, so the amplitude of this peak will be again 0.93 seconds, because here we are just recording the heart period. So for each point in this tracing, each point is the distance in time between the last detected heartbeat. Of course, for the heart rate, we can do the same. The distance will be again 0.93, but here we will have the 60 divided by 0.93, so the beat per minute. But this will be the instantaneous heart rate. Yes, maybe this is the instantaneous heart rate, but it's not uniformly sampled. You can see here, for example, the distance is shorter than here. And why? Because, of course, here the frequency is higher. So the problem with the heart period and the heart rate is that it's a signal which is not sampled at the uniform time spacing. It's not uniformly sampled. And the problem I am concerned with now is how to create a signal which is uniformly sampled to be used, for example, for fast Fourier transform or other things. Just to clarify better, you see here there are 1, 2, 3, 4 ECG peaks, and the heart period, of course, can be considered as the distance in seconds between two consecutive peaks. Here, for example, the heart period is 0.86, 0.79, 0.72, and to each one correspond a different instantaneous heart rate, if you want. But you can see that the sampling is not uniform. Of course, the sampling is changing. The sampling rate of the heart rate is changing because the sampling rate of the heart rate signal is the heart rate signal itself. So, in conclusion, we can say that the heart period is only available at each heartbeat. It's a discrete signal, but the value of the signal is available at a non-uniformly spaced instant of time. So the problem now is how to create an heart rate signal which is uniformly spaced at the uniformly spaced instant of time, instead of having the heart rate only available at each heartbeat. That's the problem we will face now. So, first statements to take home: the heart rate signal is a time discrete signal, sampled, whose samples are only valuable at discrete, non-uniformly spaced instants of time. So we have a non-uniform sampling rate. You know that the heart rate signal, I think, is the only biological signal which is only available in sampled form and in non-uniform sampled form. Any further signal treatment processing requiring a uniformly timed sample signal, like for a fast Fourier transform, for example, is not possible until the heart rate signal is converted to a uniformly sampled signal. And that's the problem we have to face. Now, how to get a uniformly sampled heart rate signal, and how to get a heart rate signal sampled with a sampling frequency higher than the heart rate itself. Why I would like to sample the heart rate signal with a sampling frequency higher? Because I would like to know the heart rate signal between two consecutive heartbeats. So I would like to avoid being blind between two consecutive heart rates. I would like to have the possibility to state the heart rate signal at each instant of time, even if between two consecutive heartbeats. And also, what should be the correct sampling frequency for the heart rate signal? Well, until now there were two approximate methods used so far. So please remember, you have a series of points. Each point is the heart rate, and each point are also available at the heart rate. Okay, so the heart rate signal is sampled at the heart rate itself. If you want a uniform sampling, one of the possibility is to take the average heart rate in the time epoch you are working on. Second, take the inverse of the average heart rate, so you have the average heart period, and use it as the uniformly spaced samples. But of course, in that case, each sample will not be superposed, will not correspond to the actual sample from the heartbeat detector. So you have two possibilities, because there are two approximate methods. One is to shift the closest true heart rate value on the closest uniformly spaced sample. So you have to shift and say, well, now at this point, the value is the closest point of the heart rate, or interpolate the closest true heart values to the actual sample, which is not corresponding at the same instant of time when you have the actual and true heart rate. Well, this kind of methods are quite approximate and are not very good for studying variation in time of heart rate, or even for studying Fourier transforms. So this means the oscillation of the heart rate, because you are introducing a quite important jitter in approximation in the position of the heart rate signal, and this will affect the actual final treatment of the signal. So, as a matter of fact, estimating the instantaneous frequency of a signal is a contradiction. Because any signal of which you are interested in the instantaneous frequency, you need to count, you need to integrate. You have to count the events, cycles or heartbeats or whatever for a given time, and then divide the counting by the time duration. So it seems, in fact, that the instantaneous frequency estimation of any signals seems impossible. But we can do something. And for introducing these methods, I would like to use the story of rabbits along the road. So I will introduce this story so that you can understand better, and then we will chant the rabbits with the Ecg. Now, suppose that you are running on a straight road, and from time to time you cross a few rabbits aside along the road, and you are interested to know how many rabbits per mile are there. Hence, the frequency of rabbit as measured in rabbits per mile. Now, suppose you found 2 rabbits along the first mile, 3 rabbits along the second mile, 1 rabbit along the third mile, 2 rabbits along the fourth mile, 1 rabbit along the fifth mile. And at each milestone, you can say that the frequency of rabbits was accordingly 2 rabbits per mile on the first mile, 3 rabbits per mile on the second mile, and whatever. But what was the rabbit frequency at mile 2.7, for example, when maybe the 5th rabbit was not crossed yet? Well, let's sketch the situation. So we have this is the road, and you have milestones on the road, and the milestones, please be attentive, the milestones are placed are uniformly spaced along the road. The rabbits, by the way, are not uniformly spaced along the road. There are 2 rabbits here, 3 rabbits here, 1 rabbit here, 2, 1. Now, from here, we are starting looking for rabbits. On the first mile, we saw 2 rabbits. On the second mile, we saw 3 rabbits. On the third mile, we saw 1 rabbit, 2 rabbits on the fourth mile, 1 rabbit on the 5th mile. Well, the method for estimating the instantaneous frequency of a signal. So the method for estimating the instantaneous frequency of rabbits per mile is the following. First, we count the total crossed rabbits from the start and recording the count at each milestone. So at the start, we have the 0 mile, 0 rabbits. At the first mile, we found 2 rabbits. At the second mile, we found in total 5 rabbits. The third mile, we found 6 rabbits, 2 plus 3 plus 1. At the 4th mile, we found 8 rabbits. At the 5th mile, we found 9 rabbits, and like this. Now, you note that the rabbits are not uniformly distributed because they are located at random along the road. Milestones are uniformly distributed. They are located at each and every mile. Frequency of rabbits is changing at each mile. And you can define a rabbit frequency at each mile or on average on the 5 miles. And you cannot define an instantaneous rabbit frequency, rabbits per mile, as you only know the average rabbit frequency at each mile. Now, how to estimate an instantaneous rabbit frequency? Take a look at the running count of rabbits. On the first mile, we have 0 rabbits. On the first mile, we have 2. On the second mile, we have found 5 rabbits. On the third milestones, we found 6 rabbits. On the 4th milestones, we found 8 rabbits in total. And on the 5th milestones, we found 9 rabbits in total. This is the running count of rabbits found during running on the road. Now, if we take the derivative, the first derivative of this running count, we have this signal, which is somewhat a derivation, first derivative of this. And you can find that, as a matter of fact, we have a sort of estimation, or local estimation and continuous estimation of the frequency of rabbits along the miles, not waiting for the actual number of rabbits at each milestones. So the red curve is somewhat we can interpret as the instantaneous frequency of rabbits along the road. And this is the first count of rabbits. Now, how we can come back to the heart rate? Of course, each rabbit equal an heartbeat. And each milestone is the uniformly spaced sampling times of the heart rate signal. Okay, so instead of running the road, we are just leaving the time, and during the time, from time to time, we will detect a rabbit, or we will detect an heartbeat. At each heartbeat, we count the heartbeat, and we record the total number of heartbeats found at each milestone. Of course, this signal, the running count of rabbit or the running count of heartbeats, this signal will be a non-decreasing signal, because will be always summing up, at least 0, but it will be always growing. Okay, now look at what we can do. In the first place, we have, on the first tracing, we have the Ecg signal with all the Ecg and all the QRS, all the heartbeats detected. On the second signal, we have the running count, that is the pulse count. Of course, we start from 0 and we go on. And please note that this pulse count signal is uniformly distributed, is uniformly sampled, because we, at each instant of time, uniformly spaced, we put the number of beats detected until that instant of time. And of course, this signal is just always growing up. Of course, the speed of growing up, the slew rate of this signal will depend on the local frequency of the heart rate, of course, because if the heart rate is going up, this count, this running count will be steeper, will have a higher slow rate. If the heart rate is going down, then the signal we will have a lower slow rate. Now we will take the first derivative of this signal, and the first derivative of this signal will give us the instantaneous heart rate. And you can see something that cannot be seen by the naked eye here. Here you can see the variation in time of the heart rate. This means, for example, that in this place, at 0.45 seconds, there is a peak. This means the heart rate is higher here. And this means that in this place, we have a denser number of ECG, or a denser number of heartbeats. Of course, there is some artifact at the beginning, at the end, because of the derivation of the derivative we found. But look, we started from the ECG, we detected all the heartbeats, which is like rabbits, randomly distributed, more or less randomly distributed, and we found the heart rate signal uniformly sampled, because here we used a uniform sampling frequency, and you can see the variation in bit per minute is changing, and maybe this variation will be due, for example, to the parasympathetic and sympathetic activities. Typically, the variation of the heart rate is given by the breath rate, which is changing the heart rate. Just to have an idea, here we found 0.1, 0.2 at 23 seconds, 0.09 to 23 seconds, 0.83, and the instantaneous heart rate here should be 81 beats per minute, and the signal gives us 82, so it's a very good approximation. And here, for example, we have 1 point at 35.16 seconds, and the second point is at 36.09 seconds. And this means that the heart rate in this place should be around 64, is 67. So it's quite good. Of course, this heart rate has been smoothed regarding to the instantaneous heart rate, but it's continuous heart rate. We can detect the heart rate wherever. You see, now I put the data tip here between the two. This means that I have an idea of what is the instantaneous heart rate, even if I'm not exactly at the position of each heartbeat. Now the problem of the differentiator, because I know that I have seen that I've said that we need to differentiate the running sum for obtaining the heart rate. And the problem of the differentiator is quite important, because differentiating a signal numerically is very difficult, because creating a reliable derivative of the signals is normally a noisy process, so we should avoid enhancing too much noise, and also use a reasonable amount of computing power. We can use a filter for differentiate. As a matter of fact, you can see here is a typical differentiator. That is the value of the signal at point n minus the signal at point n minus 1 divided by the sampling period, and this will give us the derivative. This is clearly the numerical first derivative of the signal. Why this is a filter? Because in the zeta domain, this is a filter like this. It's an all-zero filter. And the Bode plot will give us a signal Bode like this, where the magnitude of the filter is something like this. And you can see it's just a line at low frequency. At high frequency going to the Nyquist frequency, the signal will change. But for low frequencies, and we are interested in low frequencies, we have just a straight line. Of course, because the derivative is just a straight line at low frequency. As the higher the frequency, and the higher will be the derivatives, because the higher the difference, the higher will be the derivative. Okay, so this is completely normal. But the problem is that we have also a very high magnitude for high frequencies, for noise. So for avoiding this, we should consider another differentiating filter, for example, a fourth order filter like this one. And the Bode plot of this filter is something like this. At low frequencies is still a good differentiator. At the high frequencies is an integrator. So it's a passband, as a matter of fact. As an integrator at high frequency means that the noise will be eliminated for high frequencies, but the low frequencies where we are interested, the filter still acts as a derivator. And we use this kind of filter for detecting this activity. So we are able to detect the variation in time of the heart rate. Now, I'm at the end of the presentation, and I would like to introduce you two of my students, Harish Kambampati and Amit Kumar Ramakrishnaya. Harish is my student coming from Vijayawada, and now he is a PhD student in Rome Tumbergada University under my tutoring, and also Amit Kumar Ramakrishnaya is a Master of Science student in Rome Tumbergada University, and he comes from Bangalore, Karnataka. And they are using these methods for detect the evoked response of the autonomous nervous system. What is the problem now? The autonomous nervous system acts on the heart rate. So by detecting the variation in heart rate, we can have an idea of what is the level of activity of the autonomous nervous system. The idea was to study the real-time response of the autonomous nervous system when the subject is exposed to scary video scenes. So for stimulating the parasympathetic and sympathetic activity, we created or we found on the web some scary video scenes from scary films or horror films, and we proposed these scenes to some some other students, and at the same time we are detecting the heart rate, and we would like to find the variation in heart rate when the scary video scenes appear, and also to understand what is the time lag between the appearance of the activity of the autonomous nervous system on the heart rate. And you can see here, for example, it's a typical situation in which we have here some 75 seconds of the signal. We have all the pulse count, the derivative, and then here you can see the heart rate changing at point 45, and at 45 seconds exactly the scary video scenes appeared. And so we can understand what is the rise time of the heart rate following a scary video, and what is the recovering of the heart rate after the scary video. And so this is an activity due to the autonomous nervous system, and we can compare and classify different patients having different responses of the autonomous nervous system to scary video images. Here, for example, you can see different scary videos appearing in different parts of the video. In this case, the heart rate here is the square of the heart rate to better put in evidence the signal. Also here, you can see with almost 5 or 6 minutes video, you can see where there is some emotionally stimulating video sequences or video images. You see the heart rate is changing very fast, very immediately, and this is very nice. We can detect the variation of heart rate in real time using this method. I think that this is one of the first times that the heart rate is used in real time. Most often, until now, heart rate variability has been done using the spectrum, using the fast Fourier transform. And here you can see also the fast Fourier transform of the same sequence. But now we are much more interested in real-time evoked responses from the autonomous nervous system. And I think that using the heart, this is the first time we are able to record evoked response from the autonomous nervous system. Now I thank you for your attention, because of some 1 hour I'm talking, and if there are any questions, I can reply to you, and also, of course, I will share this presentation with the participants. So, thank you very much. Please, it's up to you to reply.
Thank you, Professor Staderini, for the talk. Now, we will move on to the question session. Participants can either use your microphones from their device or may post their question, praise in the chat box. Okay, it seems like any questions?
Or maybe you can also share my email, so that if I any question, they can forward me any question by email if they want.
Thank you, Professor. It seems like we have come to the end of our session. Now, let me take this opportunity to propose a vote of thanks. I, on behalf of St. Joseph's Engineering College. Excuse me.
I have seen that there is a question from Professor Mijai Mohammed. regarding the methods available in video perfusion technology. In video perfusion technology is a technology which is able to detect the the variation in the color of the skin because of varying perfusion of the skin. Maybe if you are interested, I can show you. I can show you a video like this. If we have time, I can show you a video regarding this. Let me see the video. I'm looking for the video because it's very nice. And where is the video? Yes, I'm about to come for the video. Medical device. No. Miscellaneous data sheet. Let me see, because I have somewhere here. Video recordings, device definition, no. No. Course material, yes, heart rate censored, heart rate introd. Okay, maybe. Yes, I have now. Zach, I can. But wait. Okay, share the screen. No. Okay. You see the screen now?
No, sir.
Okay. You can see now you can see the screen and the variation in the color of the skin.
Not yet, sir. I'm sorry.
Okay. Yeah. Now you should see.
Yes, Professor.
You should see now.
Yeah.
Still not seeing. Share entire screen. Okay, now you're seeing. No. Not at all. New share, select window, entire screen. Allow. Well, I will send you the video because now there is some problem in showing you the video. I will show you.
It can be seen, sir.
Because I'm sharing the entire screen, you should see.
Yeah, we could
see the video
screen.
now.
Yeah. Yes, sir. We could see it now.
Now, you see, this is the video, the video skin recording. there is a particular treatment of the image. You can do this using a standard webcam, and there is a particular color amplification of the signal, so that you can detect the heart rate using the variation in color. Of course, you have to amplify the color variation on the skin of the subject, and you will see the heart rate. You see now. Okay, now stop sharing. Okay.
Professor?
Yes?
You have got one more question from Tejal Tom. Shall I raise a question?
What?
You have
Please?
got one, Professor. You have got one more question from one Tejal Tom.
Yes.
Shall I raise a question? Yeah. Is PCG well suited for detecting the murmur?
Yes. Let me see. Let me see the PCG is well for detecting the murmur. Yes. Yes. The PCG is very good for detecting the murmur, because the phonocardiography is a quite important method for detecting this. There are a series of commercial instruments regarding this. There are also a lot of studies regarding the use of PCG for detecting the murmur, and often you can also record the PCG and send the PCG by a smartphone, so that the cardiologist can detect this. I was working on the PCG a few years ago, and I found that it's also possible to detect to make the fast Fourier transform of the PCG, and with a short fast Fourier transform, you can also detect the variation of the frequency of the heart sound, not just the murmur, but also the frequency of the heart sounds. And from the variation of the frequency of the heart sounds, you can have an idea of the state of the valve. And so it's also important to make diagnosis of the tissue viscosity of the valve in the heart, and that's something very interesting, much more interesting than detecting the murmur. Detecting the variation of the tissue viscosity, viscoelasticity of the valve of the heart. It's a quite important diagnostic methodology to detect some disease of the heart, which may arrive earlier than the presence of murmurs.
Okay, thank you, Professor. Thank you for your answer. Any more questions? I think we have covered all the questions. Now, let me take this opportunity to propose a vote of thanks. I, on behalf of St. Joseph's College of Engineering and Technology, extend my sincere gratitude to Professor Enrico Staderini for giving the valuable insights on the problem of recording instantaneous heart rate signal. As a token of gratitude from our end, please do accept a virtual memento that will be shared right now.
Thank you.
Yeah. Thank you, Professor.
Thank you very much.
Yeah. I would like to once again thank everyone who made this meeting possible. Thank you, one and all.
Thank you very much. Hopefully, I would like to visit your university sometime. Maybe next year I will travel to India, and I would like to also to visit St. Joseph's College of Engineering and Technology. I had already contacts with the people in Tamil Nadu, but not in Kerala. maybe I will go to Kerala from Tamil Nadu, and maybe we can meet sometime next year.
Thank you, Professor. You're most welcome.
Okay.
Yeah. Now you end the call, Professor. You're done.
Okay. Thank you very much. Bye bye.
Thank you so much for your time, Professor.
Thank you. Bye bye.
Yeah.